Okay, geometry. We're jumping ahead a few sections. We're going to knock out section 9-8. We are going to do the sections in between, but given where we're at and what the schedule looks like looking ahead, I'm going to jump ahead to 9-8 right now. The Pythagorean Theorem and what they call space figures is really going into 3D figures. So whenever a problem mentions a rectangular solid, then it's a 3D box shape, and I got a little space. I'm going to draw one out in just a second. There's going to be 6 what they call rectangular faces. That's the sides of it, like the top, the bottom, the left, the right, the front, and the back. Picture holding a box right in front of you. If you're holding a box, you got a left, right, front, back, top, bottom. If you're holding a box type shape. There's going to be 12 edges. That would be like everything that frames out one of the rectangles on one of the sides. Edges that go up and down, edges that go left and right, edges that go from the back to the front and front to the back. And what we're going to concentrate on are these 4 diagonals of the solid. So without further ado, if you don't know how to draw a 3D box, I always picture like grade school kind of working on this for some reason. Draw with some sort of perspective. You're trying to draw the front face. Easy to say. Draw the front face. It's just a regular rectangle. And I'm going to put a few, you should look parallel. Go a little longer, a little longer. Okay. I'm doing all these so that they almost look parallel to each other. All right. And they're all about the same length, but I'm putting them on a slant to give it that 3D kind of a look. Then I'm going to draw a line across, and that line should look parallel to this one. I'm going to help fix the corners there. I'm going to go straight down. Not the best one I've ever drawn. So that's 3 of the sides that you can see. You can see the top, you can see the front, you can see the right side. If it was like a solid brick, you wouldn't be able to see the back side. But we need to make it look almost like transparency. The back edge would look like this coming down. All right, and we would have this come across, and they would meet. And then this would go to here, and it gives us that 3D effect, that 3D look to it. Every corner should be labeled with the capital letters. So I'm going to go alphabetical. A, you got to put them in the same spots. A, B, C, D, and then go E, F, G, and H. All right, so when they say edges, so some of the edges on here would be like AE is an edge, that segment. BC is an edge, that segment. Even the ones that are in the back, like GF. GF is an edge. All right, there's 12 of them total. Left, right, up, down, everything in solid green, even the dotted green. Those are the edges of the box. We want to learn how to find the diagonal of the box. So the diagonal of the box, and there are 4 diagonals of the box. Those diagonals in this diagram is BH, if that was drawn in, EC, if that was drawn in, E all the way up to C, F to D, if that was drawn in, and A to G, if that was drawn in. All right. Now, it has more to do with like my diagram not looking so hot, but all four diagonals are congruent. Now, if I were to draw all 4 in, they probably wouldn't look all that much congruent, but if I were to draw B down to H, all right, I can do the same thing and draw like E up to C or A down to G. Because we made it like 3D, if you actually draw them in, you're not looking at it flat. Perspective-wise, they're not going to look congruent to each other. But all 4 of those, if they were drawn in, would be congruent. So it would be like the front left bottom corner to the back right upper corner. That's E to C. That's a diagonal of the solid. All right. Diagonals of the solid, not a diagonal of a face like A to H. That's just a diagonal of a face of one of the rectangles. This goes right through the solid brick part of this. All right, so how do they set these kind of problems up? So a diagonal problem in a rectangular solid. So it would look something like this, an example 1. Example 1 would say the dimensions of a rectangular, and that's just letting you know all the sides are rectangles of a rectangular solid is 8, 5, and 3. Find the length of the diagonal of the solid. So they even have to be specific as to like, well, which diagonal do you mean? Do you mean a diagonal of one of the faces, the diagonal of the right side of it? We want a diagonal of the entire solid, diagonal of the solid. So when they give you numbers like this, 8, 5, and 3, those are your dimensions. That's your length and your width and your height. And you can actually mix those up. You can put them any way you want. It won't change what the diagonal length is. So that's kind of interesting. I call 8 my length, 5 my width, and 3 my h, and draw it out, my height. And another kid can do it backwards and say, well, 3 is my length and 5 is my width. So instead of the rectangle looking like this, the other kid's rectangle might look straight up and down. It might look taller rather than wider. But the diagonal that's drawn in the middle, the diagonal in the middle will end up being the exact same length. So that doesn't ruin the problem. Now, I really do usually go length and width and height. So length is 8, would make it kind of a long, along the front, let's say, that's 8. 5 would be the width, so that would be this way, and 3 would be the height, which isn't really all that tall. So I usually draw the front rectangle. I don't know why I didn't do that this time. Let's see, it doesn't look so hot. Go like this and like this. And now I got my, this one back side looks a little crooked, but got my rectangular solid. Yeah, I forgot my numbers. Length, width, height. Now, well, I probably should have talked about it maybe on this diagram up above, but all the height lines are going to be the same. So AE is the same number as DH, is the same number as CG and BF. All the length numbers, EH, AD, BC, FG, because they're rectangles, all right? Because they're rectangles, they're all going to be the same number, all right? They're all opposite sides of one of the rectangles. And then even going to the back, from the front to the back, HG is the same length as DC, is the same length as AB. So when I do this down here, this 5 goes for here, for here, for here, and here. This 3 goes here. I can put it here. I can put it here. I can put it here. Now, that's, whatever you pick for your height number, that's really going to be an important number. So this is a two-step process. Two-step process. So first step. First step is find the diagonal of the floor. Find the diagonal of the floor. So the diagonal of the whole solid, now I should have drawn that in with my original diagram. So what I'm looking for, and I can draw any one of these diagonals in, but I'm going to do from this corner to this corner. So that's what we're looking for. I'll call it small d we're looking for. We're looking for that diagonal. First step is to find the diagonal of the floor. What we're going to do is create a triangle, a right triangle that's standing up inside. So I'm going to connect on the floor this diagonal across the floor. Now there's another one going the other way, but I want to create a right triangle that's standing up inside here. So the floor has these two dimensions, an 8 going across and a 5 going this way. And I just drew this diagonal. And we're going to use Pythagorean Theorem in order to find this number. It's not going to be a nice number. So 5 squared plus, this is obviously a right angle, plus 8 squared equals c squared. 25 and 64 equals c squared. So if I add 20, it's 84. 89 equals c squared, square root of 89. Now, for this problem, I could leave it the square root of 89. I don't need to look to break it down. I don't even know if it does break down. But just leave it the square root of 89, and you'll see on the next step is why you don't need to break it down. That's not your final answer. That only gives you the number of this diagonal on the rectangle on the floor. All right, now step 2. Step 2 is pretty darn important. Step 2, find the diagonal by using Pythagorean Theorem for standing up triangle. You're going to use the Pythagorean theorem for the triangle that's standing up in the middle. There's a triangle standing up in the middle of this whole thing. What you have is a 3, a square root of 89, and D. There's a triangle that's standing up, a right triangle. You have a 3 for one leg, a square root of 89 for the other leg, and the diagonal is what we're looking for. So if I do the Pythagorean theorem, excuse me, I'm going to try to squeeze in the work here. 3 squared plus square root of 89 squared equals the diagonal squared, D squared. So that's going to be 9. And this is why I didn't want you to simplify it. You're going to square it anyway on the next step. So the square root of 89 squared is 89. Now, on this last step, if this comes out to be, let's see, 9 plus 89, it's going to equal 98. This we need to simplify. All right, so when we square root that, I'll take the work, put it up here. The diagonal is going to turn out to be, well, the square root of 98 is actually not that bad. You're going to split it in 2, and you get 49 times 2. So the diagonal is 7 square root of 2. Like if 98 didn't simplify, you would just leave it square root of 98. But it's going to be 7 square root of 2 for this diagonal. It's going to be easy for me on a quiz or a test to like make up other problems. All I'm going to do is give you different numbers for the 8 and the 5 and the 3. Find the dimensions of a rectangle. If it's just, 10, 7, and 4, then you're going to do the same thing and just deal with the square roots that are involved as you're going along. So that's one of the 3D shapes we're going to deal with. The other 3D shape that we're going to deal with is a pyramid. Kind of like the ancient pyramids you see. Ancient Egypt comes to mind, Aztec pyramids, stuff like that. So there are different pyramids. Like the bottom of a pyramid could be like a triangle or something like that. Oh, I forgot it. Before I get into pyramids, I just turn my notes over. Just one little quick. A cube is a rectangular solid where all sides are squares. So I guess it comes up either on a quiz or test or homework. I just have a little thing on my notes from last year or last few years. If they ask for a cube, then all the sides are the same. They'll only give you one dimension because the length, the width, and the height are all the same. So they might just say the edge is 15. Well, what that's telling you is that everything is 15, right? Every edge you can see on there is 15 because it's a cube and not just a normal rectangular solid. All right, jump over to part 2 of the notes to get the rest of it with the pyramid example. Pyramid example is coming up next.